Imagine a world gripped by the suffocating darkness of global conflict, where the fate of nations hung precariously on the slender threads of whispered intelligence and the impenetrable walls of enemy encryption. In the chilling shadows of World War II, amidst the roar of bombers and the silent menace of U-boats, a silent, intellectual war raged, a battle of wits fought not on bloody battlefields, but within the confines of hushed rooms, against the relentless logic of machines. This was a time when the seemingly abstract realm of mathematics and logic held the terrifying power to tilt the scales of human destiny, where the ability to decipher encrypted messages could mean the difference between victory and devastating defeat. The sheer complexity of the enemy's ciphers, particularly the German Enigma machine, presented an almost insurmountable intellectual barrier, a labyrinth of permutations and combinations designed to render their communications utterly secure, giving them a terrifying advantage in the brutal dance of modern warfare. For years, the Allies wrestled with this enigma, knowing that vital intelligence lay hidden within its coded messages, yet lacking the key to unlock its secrets. Yet, within this crucible of intellectual struggle, a singular mind emerged, a figure whose quiet brilliance would not only crack the unbreakable codes of the enemy, but also lay the foundational conceptual groundwork for an entirely new era of human ingenuity, the age of artificial intelligence. This was Alan Turing, a name that resonates with both profound intellectual depth and a tragic irony, a visionary whose abstract theories and practical innovations would shape the very fabric of the modern digital world. He was an individual who saw not just the immediate military application of computational power, but the boundless, philosophical implications of machines that could think, learn, and even converse, blurring the lines between human and artificial cognition. His laboratory, whether the theoretical constructs within his mind or the bustling, top-secret wartime facility at Bletchley Park, was a crucible where abstract logic fused with engineering necessity, producing insights that were decades, sometimes a century, ahead of their time. From the theoretical Turing machine that underpins all modern computation to the practical cryptanalytic bomb machines that shattered the Enigma code, and later, to the Turing test that continues to define the very essence of machine intelligence, Turing's fingerprints are indelibly etched upon the bedrock of our digital age. Yet, for all his undeniable contributions and the lives he undoubtedly saved, a shadow of injustice and unfulfilled potential hangs over his legacy, particularly concerning his later, more ambitious, and seemingly utopian endeavors in the realm of machine intelligence. The echoes of his grandest visions, especially those concerning the potential of thinking machines, continue to captivate and intrigue, sparking debates and inspiring generations of computer scientists and philosophers. Was he a misunderstood prophet, a visionary whose genius was simply too far ahead of its time? Or did he touch upon fundamental truths about the nature of intelligence that remain largely unexplored or even suppressed? This is the extraordinary journey into the life and mind of Alan Turing, a man whose brilliance broke wartime codes and, in doing so, unknowingly laid the intellectual groundwork for a future where machines could emulate human thought. Prepare to explore the fascinating paradox of a genius who both grounded us in the grim realities of wartime intelligence and beckoned us towards a future where artificial minds might one day stand alongside our own. His story is a compelling blend of groundbreaking intellectual achievement, societal prejudice, profound philosophical inquiry, and a persistent whisper of what might have been, a legacy that continues to spark curiosity and inspire the imagination of those who dare to dream beyond the conventional. Chapter 1. The Cosmic Enigma, the Birth of a Black Hole. To understand Stephen Hawking's monumental contributions, we must first embark on a journey into the life cycle of a star, tracing its evolution from a brilliant cosmic furnace to the terrifying, final act that births a black hole. This process, governed by the elegant yet brutal laws of gravity and stellar physics, is the origin story of the universe's most mysterious objects. It begins with a nebula, a vast cloud of interstellar gas and dust, a cosmic nursery where gravity, the great architect of the cosmos, begins its relentless work. Over millions of years, gravity pulls this matter together, compressing it, and as the density and pressure increase, the core of this nascent star ignites, triggering the process of nuclear fusion. This ignition marks the birth of a star, a brilliant equilibrium between the inward crushing force of gravity and the outward push of radiation pressure from the fusion reactions in its core. This stable, luminous phase, known as the main sequence, can last for millions or even billions of years, a star's energy a continuous testament to this delicate cosmic balance. However, this stable period is not infinite. As the star ages, it begins to exhaust its nuclear fuel. For stars with a mass comparable to our Sun, this process leads to a relatively gentle end, with the star expanding into a red giant and eventually shedding its outer layers to become a white dwarf, a dense, cooling stellar remnant. But for stars that are significantly more massive, typically more than 20 times the mass of our Sun, the end is far more dramatic and violent, a spectacular cosmic catastrophe that sets the stage for a black hole. When such a massive star exhausts its fuel, the delicate balance between gravity and radiation pressure collapses. Gravity, now unopposed, takes over with a vengeance, pulling the star's immense mass inward at incredible speeds. This inward collapse triggers a cataclysmic event known as a supernova, one of the most powerful explosions in the universe. For a brief, brilliant moment, the star outshines its entire galaxy, releasing an astonishing amount of energy and scattering heavy elements forged in its core across the cosmos. But the core of the star continues its relentless collapse. If the remaining core mass is between approximately 1.4 and 3 times the mass of our Sun, gravity crushes it into an incredibly dense object called a neutron star, where protons and electrons are squeezed together to form a solid mass of neutrons, packing the mass of a star into a sphere the size of a city. The birth of a black hole, however, requires an even more extreme endpoint. If the remnant core of the star after the supernova is more massive than about 3 times the mass of our Sun, there is no known force in nature strong enough to halt its collapse. Not even the quantum degeneracy pressure of neutrons can withstand this gravitational onslaught. The core collapses further and further until all of its mass is compressed into an infinitesimally small, infinitely dense point known as a singularity. Around this singularity forms a region of space-time from which nothing, not even light, can escape, the event horizon. The black hole is born, a region of space-time where the curvature of space is so extreme that all paths, including those of light, lead inexorably towards the central singularity. The black hole is therefore not a physical object in the traditional sense, but a region of space-time defined by its gravitational properties. Its size, measured by the radius of the event horizon, is determined by its mass. The event horizon is a point of no return, a one-way cosmic membrane where the escape velocity, the speed needed to overcome gravity, exceeds the speed of light. From an outside observer's perspective, an object falling into a black hole would appear to slow down and freeze at the event horizon, its light becoming redshifted until it fades from view entirely. The information of the object's final state seems to be lost forever, a profound paradox that would later become a central focus of Stephen Hawking's work. This incredible journey from a brilliant star to a silent singularity sets the stage for the intellectual battles that Stephen Hawking would wage. The black hole, a product of a star's death, was for a long time considered an endpoint, a static and unyielding devourer. It was a puzzle that seemed to challenge the very laws of physics, a place where matter and information disappeared forever. It was this profound cosmic enigma that would capture the imagination of a brilliant young physicist and lead him to some of the most startling and revolutionary conclusions in the history of science. The black hole, a product of gravity's ultimate triumph, was ready for its most profound challenger. Chapter 2: The Young Maverick, Hawking's Early Life and Diagnosis. Before he became a global icon and a symbol of intellectual resilience, Stephen Hawking was a young man of immense promise and unbridled curiosity, an unconventional mind drawn to the deepest questions of physics and cosmology. Born on January 8, 1942, exactly 300 years after Galileo Galilei's death, Hawking's early life was marked by an independent spirit and a love for exploring the fundamental principles that govern the universe. He was born into a family of highly educated individuals. His father, Frank Hawking, was a medical researcher, and his mother, Isabel, was a political activist. This intellectual environment fostered a love of learning and an inquisitive nature from a very young age. As a child, Hawking showed an early aptitude for mathematics and physics, though he was not a particularly neat or organized student. He reportedly took a long time to learn to read and struggled with handwriting. His mind, however, was in a constant state of exploration, fascinated by how things worked. He and his friends would build rudimentary computers from old clock parts and salvaged components, a testament to his innate mechanical aptitude and his relentless desire to understand the inner workings of complex systems. His passion for mathematics was so strong that he decided to major in it at Oxford University. Even though they did not offer a degree in the subject at the time, he pursued a degree in natural sciences instead. His time at Oxford was a period of both academic excellence and social nonchalance. He found the undergraduate curriculum ridiculously easy and often did not feel the need to apply himself to a rigorous study schedule, as his brilliant mind could grasp concepts with a profound, intuitive ease. Despite his laid-back approach, he was a member of the university's rowing team, a challenging physical pursuit that provided a counterpoint to his intellectual endeavors and demonstrated a youthful physicality that would tragically be short-lived. After his 3 years at Oxford, he was awarded a first-class degree with honors. He then moved to Cambridge to begin his postgraduate studies in cosmology, where he initially felt a bit lost and a touch underwhelmed by the university's reputation. He was looking for a topic for his PhD thesis, something that would truly challenge his intellect. It was during this time, in his early 20s, that the first signs of a devastating illness began to appear. Hawking began to experience clumsiness, stumbling, and difficulty with simple tasks like tying his shoes. A fall down a flight of stairs during a holiday break led him to seek medical attention. In 1963, at the age of 21, he was diagnosed with amyotrophic lateral sclerosis, ALS, also known as Lou Gehrig's disease, a progressive neurodegenerative disease that affects nerve cells in the brain and spinal cord, leading to muscle weakness, paralysis, and eventually, death. The prognosis was grim. Doctors gave him only 2 to 3 years to live. This diagnosis was a profound shock, casting a dark cloud over a life that had been so full of promise and physical vitality. Initially, the diagnosis plunged Hawking into a deep depression, causing him to withdraw from his studies and his friends, seeing little point in continuing his work if his life was so limited. However, a pivotal moment of intellectual and personal reawakening came when he began to develop a relationship with Jane Wilde, a fellow student he had met at a party. Their engagement and subsequent marriage in 1965 gave him a powerful reason to live and to fight the disease, inspiring him to return to his studies with a newfound vigor and purpose. He realized that he could use his brilliant mind to explore the cosmos even as his body failed him. This period of his life, a harrowing juxtaposition of intellectual blossoming and physical decay, was the crucible in which his extraordinary journey was forged. He found his purpose in his PhD research, guided by his supervisor, Dennis Sciama. The topic that captivated him was the nature of cosmic singularities, the points of infinite density predicted by Einstein's theory of general relativity, particularly the singularity at the beginning of the universe, the Big Bang, and the singularity at the heart of a black hole. The intellectual fire ignited by this challenge, combined with his unwavering personal resolve, would propel him to achieve scientific breakthroughs that defied all expectations. The young maverick, facing a grim prognosis, was about to embark on an intellectual quest that would challenge the universe itself, proving that the greatest voyages of discovery are often not physical, but intellectual. Chapter 3: The Singularity Theorems, a partnership with Penrose. Following his devastating diagnosis, a diagnosis that paradoxically ignited a new sense of intellectual urgency within him, Stephen Hawking embarked on his postgraduate work with a singular focus on the nature of cosmic singularities. He joined a burgeoning field of research that was wrestling with the profound implications of Einstein's general theory of relativity, a theory that predicted the existence of singularities at the heart of black holes and at the beginning of the universe itself. It was during this period that he forged a crucial and highly productive intellectual partnership with the brilliant mathematical physicist Roger Penrose, a collaboration that would fundamentally reshape the understanding of gravity and spacetime. Before their work, many physicists viewed singularities as mere mathematical artifacts, a flaw in the equations of general relativity that would likely be resolved by a more complete theory of gravity. They believed that a collapsing star, for example, would somehow halt its collapse before reaching an infinitely dense point. Penrose, however, had already made a groundbreaking discovery in 1965, proving that a collapsing star of sufficient mass would inevitably form a singularity. This was a revolutionary insight, but it applied only to the gravitational collapse of a star. The question remained, did a singularity also exist at the beginning of the universe? And were these singularities truly unavoidable predictions of general relativity? Turing and Penrose began to collaborate in the late 1960s, their complementary skills creating a powerful synergy. Penrose's expertise in topology and global geometry provided the conceptual tools, while Hawking's deep understanding of differential geometry and his relentless computational drive provided the mathematical muscle. Together, they sought to prove that singularities were not just a consequence of a specific type of collapse, but a general and unavoidable feature of a wide class of spacetimes, including the universe itself. This collaboration led to a series of groundbreaking papers, culminating in their famous singularity theorems. The singularity theorems, often referred to as the Penrose-Hawking singularity theorems, demonstrated that under certain reasonable physical conditions, a singularity is inevitable. Specifically, they proved that if the universe is governed by general relativity and contains a certain amount of matter and energy, then spacetime must have had a beginning. A singularity known as the Big Bang, and that black holes must contain a singularity at their core. Their work was a monumental confirmation of Einstein's theory, showing that its predictions of singularities were not flaws to be fixed, but genuine features of the cosmos. The theorems were a powerful rebuttal to those who sought to explain away these extreme endpoints. Hawking's specific contributions were particularly profound. He applied the theorems to the entirety of the universe, arguing that if general relativity holds, then the universe must have begun from a point of infinite density and curvature, the initial singularity of the Big Bang. This provided a rigorous mathematical proof for the Big Bang theory, moving it from a plausible model to a robust, almost inevitable consequence of our best theory of gravity. This was a remarkable intellectual achievement, particularly for a young man who was battling a debilitating disease. As his body failed him, his mind was proving that the universe itself had a definite beginning. The collaboration with Penrose was not without its challenges. Their differing approaches, Penrose's more geometric, Hawking's more analytical, sometimes led to spirited debate, but their shared passion and mutual respect allowed them to push the boundaries of their field. The result was a synthesis of ideas that proved that general relativity, a theory of gravity, had a profound and universal predictive power, even in the most extreme conditions. The singularity theorems became a cornerstone of modern cosmology, providing a rigorous mathematical framework for understanding the origins and ultimate fate of black holes and the universe. This period marked the true blossoming of Hawking's genius, showcasing his ability to take a complex, abstract problem and provide a powerful, elegant solution. He had proven that the singularity, the point of no return for a black hole, was not a mathematical anomaly, but a fundamental feature of the cosmos, a concept that would become his primary obsession and lead to his most famous discoveries. His partnership with Penrose had not only confirmed Einstein's predictions, but had also set the stage for an even more radical idea, that black holes might not be the irreversible, static devourers they were assumed to be. The singularity theorems were just the beginning of a larger intellectual journey into the heart of cosmic darkness. Chapter 5: The Information Paradox, a Cosmic Conundrum. Stephen Hawking's groundbreaking discovery of black hole radiation, which revealed that black holes were not eternally stable cosmic prisons, but instead evaporated over vast periods of time, opened a new and even more profound can of worms for theoretical physics: the information paradox. This paradox, a cosmic conundrum that would become a central preoccupation for Hawking and the wider physics community for decades, fundamentally challenged the cherished principles of quantum mechanics, particularly the law that states that information can never be truly destroyed. It presented a head-on collision between our two best descriptions of the universe, general relativity and quantum theory, in the most extreme of environments. According to the tenets of quantum mechanics, information is a conserved quantity. The state of a system can change, but the total information describing it, the precise arrangement of every particle and every field, is never truly lost. It might become scrambled and dispersed, but in principle, it could always be reconstructed from the pieces. This is a foundational principle of quantum theory, known as unitarity, and it is a cornerstone of our understanding of the subatomic world. However, Hawking's initial formulation of black hole evaporation seemed to directly violate this principle. He argued that as matter falls into a black hole, all of its information, its composition, its energy, its quantum state, is swallowed by the singularity. The black hole itself, as described by the no-hair theorem, which we will explore in a later chapter, is characterized only by its mass, charge, and angular momentum, losing all other information about what created it. As the black hole then evaporates through Hawking radiation, the particles it emits are purely thermal, meaning they are random and do not contain any information about the matter that fell in. The black hole eventually disappears entirely, and the information is gone forever. This created a profound paradox. General relativity, in predicting the existence of a one-way event horizon and a singularity that destroys everything, suggested that information could be lost. Quantum mechanics, in its bedrock principles, stated that information could not be lost. One of these fundamental laws had to be wrong, or at least incomplete. For decades, Hawking himself stood firm on his initial conclusion, famously arguing that information was indeed lost in black holes, a position that put him in direct opposition to a majority of the theoretical physics community, who staunchly defended the conservation of information. The information paradox sparked a fierce and productive debate, driving a new wave of research into the nature of black holes and the quest for a unified theory of quantum gravity. Physicists proposed a variety of ingenious solutions to the paradox. Some suggested that the information was not lost, but somehow encoded in the subtle quantum correlations of the outgoing Hawking radiation, a concept that was incredibly difficult to prove mathematically. Others proposed that the information might be stored in a quantum remnant left behind after the black hole evaporates, a theoretical object that was still a subject of intense speculation. It was a philosophical and scientific battle that played out on the global stage, with Hawking often making headlines with his provocative claims and his willingness to bet against his colleagues. This intellectual jousting, though competitive, was always rooted in a shared commitment to uncovering the fundamental truths of the universe. The paradox was a powerful engine for progress, forcing physicists to confront the deepest inconsistencies in their understanding. In 2004, in a dramatic reversal that surprised the scientific community, Hawking publicly conceded that information was not lost after all. He proposed a new, more nuanced model where the information, though scrambled and distorted, does not disappear. He suggested that the information might escape, not from the black hole's interior, but from the event horizon itself, a concept that drew on more advanced theories in quantum gravity, such as string theory. This reversal, though greeted with a mixture of surprise and relief, showed Hawking's intellectual courage and his willingness to change his mind in the face of new evidence and evolving theoretical frameworks. While a full, definitive solution to the information paradox remains elusive, the debate it sparked has been immensely fruitful, pushing the boundaries of theoretical physics and leading to profound new insights. It remains one of the most compelling problems in physics, a legacy of Hawking's audacious discovery. The black hole information paradox is a powerful reminder that our current understanding of the universe is incomplete and that a grand, unified theory of everything, reconciling gravity and quantum mechanics, remains the ultimate prize for future generations of physicists. It is a testament to Hawking's genius that his work not only answered old questions, but also birthed new, more challenging ones. Chapter 6: The No-Hair Theorem, a black hole's elegant simplicity. In the midst of his groundbreaking work on singularities and black hole radiation, Stephen Hawking also played a central role in formalizing a concept that, while initially conceived by others, he and his colleagues would elevate to a foundational principle of black hole physics, the no-hair theorem. This theorem, with its whimsical name and profound implications, elegantly described the stunning simplicity of black holes, suggesting that once an object collapses past its event horizon, all of its unique characteristics, its hair, are lost, leaving behind only three measurable properties. This was a powerful and counterintuitive idea that further cemented the black hole's reputation as the ultimate cosmic eraser of information. The concept of a black hole having no hair was first proposed by physicist John Archibald Wheeler in the 1970s. He famously stated, "Black holes have no hair," a metaphor that meant that no matter how complex or unique the star that collapsed to form it was, its chemical composition, its shape, the subtle magnetic fields on its surface, all of that information would be lost upon the formation of the black hole. The only properties that an outside observer could measure about a black hole were its mass, its electric charge, and its angular momentum, spin. Everything else was hair that was shaved off at the event horizon. Hawking, along with his colleagues and collaborators, took this qualitative idea and provided a rigorous, mathematical framework for it. They proved that according to the laws of general relativity, any stationary black hole, once it has settled down after its formation, can be completely described by just these three parameters. This was a remarkable and deeply elegant conclusion, demonstrating that despite the infinite variety of matter and energy that could form a black hole, the final product was stunningly simple. A black hole formed from the collapse of a massive star made of hydrogen would be indistinguishable from a black hole of the same mass, charge, and spin formed from the collapse of a hypothetical star made entirely of bananas and cosmic dust. The no-hair theorem had profound implications for black hole physics and for the information paradox that Hawking would later champion. If the black hole truly lost all the information about the matter that formed it, retaining only mass, charge, and spin, then where did that information go? It seemed to be a direct violation of the quantum principle of information conservation. The no-hair theorem provided the concrete, theoretical basis for the information paradox, setting up the fundamental conflict between general relativity and quantum mechanics that would occupy physicists for decades. It was the elegant simplicity of the black hole, as described by the theorem, that made the idea of information loss so compelling and so disturbing to the physics community. The theorem also had practical consequences for how physicists thought about black holes. It meant that black holes could be categorized into a small number of types based on their three defining properties. A non-rotating, uncharged black hole is known as a Schwarzschild black hole. A rotating, uncharged black hole is a Kerr black hole, and so on. The theorem provided a powerful and elegant framework for classifying and studying these objects. It simplified the equations and allowed for a deeper, more focused study of their properties, paving the way for further theoretical breakthroughs. Hawking's contributions to the no-hair theorem, like much of his work, were characterized by his ability to take a physical idea and give it a rigorous mathematical foundation. As his physical abilities continued to decline, he relied more and more on his incredible mental powers, visualizing complex geometrical and topological problems in his mind's eye. The elegance and simplicity of the no-hair theorem perfectly suited his intellectual style, a style that sought to find profound simplicity amidst cosmic complexity. While the no-hair theorem remains a cornerstone of black hole physics, modern theories that seek to reconcile gravity and quantum mechanics, such as string theory and loop quantum gravity, have begun to explore potential quantum hair or subtle deviations from the theorem at the very small scales near the singularity. However, at the macroscopic level, the no-hair theorem remains a powerful and accurate description of black holes. It stands as a testament to the fact that in the final, dramatic act of a collapsing star, all of its intricate history and complexity are ultimately erased, leaving behind an object of stunning and profound simplicity. Hawking's work on this theorem not only provided a key piece of the puzzle, but also deepened the central paradox that he would spend a lifetime trying to solve. Chapter 7: The Cosmic Censorship Hypothesis, a Universe of Order. In the vast and often chaotic realm of cosmology, Stephen Hawking, along with his intellectual partner Roger Penrose, sought to impose a fundamental principle of order upon the most extreme phenomena in the universe. This principle, known as the Cosmic Censorship Hypothesis, was a conceptual bulwark designed to prevent the universe from descending into a state of utter unpredictability and theoretical chaos. It proposed that all naked singularities, singularities not hidden behind an event horizon, are forbidden by the laws of physics. This was a profound, and still unproven, conjecture that reflected Hawking's deep-seated belief in a universe that, despite its grandeur and complexity, adheres to a set of rational, discoverable laws. The concept arose from the work on the singularity theorems, which showed that singularities were an inevitable consequence of general relativity. A singularity is a point where the laws of physics as we know them break down, where space-time curvature becomes infinite. If such a singularity were naked, meaning it was exposed to the wider universe and not safely tucked away behind the event horizon of a black hole, it would have catastrophic theoretical consequences. A naked singularity would be a point from which anything could emerge, an object with infinite density and gravity that would not be contained by the one-way barrier of an event horizon. It would be a point where the laws of physics could be violated in a way that would be observable to the rest of the universe, a violation of causality and predictability. The cosmic censorship hypothesis, first proposed by Penrose in 1969, was a bold conjecture designed to prevent this theoretical catastrophe. It stated that every singularity created by the gravitational collapse of matter is always hidden behind an event horizon. In essence, the universe itself acts as a cosmic censor, ensuring that these bizarre and law-violating naked singularities never form. Hawking enthusiastically embraced this idea, recognizing its elegance and its importance for the coherence of physics. He believed that a naked singularity would lead to a breakdown of our ability to predict the future of the universe, as anything could emerge from it at any moment. He saw the event horizon as a necessary cosmic firewall, a protective shield that preserved the order and predictability of the cosmos. The hypothesis was not a proven theorem, but a working assumption, a guiding principle that many physicists took for granted. For Hawking, it was a philosophical anchor, a belief that the universe was not fundamentally arbitrary or chaotic, even in its most extreme conditions. He and his colleagues spent considerable time trying to prove the hypothesis, but it has remained one of the most challenging and intriguing problems in general relativity. There have been theoretical scenarios, often involving hypothetical matter or exotic conditions, that seem to violate cosmic censorship, but to date, no one has been able to find a physically realistic scenario that produces a naked singularity. The debate over cosmic censorship was a fertile ground for intellectual jousting and friendly rivalry. For instance, Hawking himself, in 1991, made a famous bet with Kip Thorne and John Preskill, wagering that the cosmic censorship hypothesis was false. He later conceded the bet in 1997, after further theoretical work showed that a naked singularity could not form under physically realistic conditions. This intellectual back and forth, driven by a deep respect for the scientific process, was a hallmark of Hawking's career. The cosmic censorship hypothesis, though still unproven, is a powerful and elegant idea that reflects a deep belief in a universe of order. It suggests that even in the most extreme events, the universe finds a way to protect its fundamental laws, hiding the chaotic singularity from direct observation. This principle had profound implications for the nature of black holes, suggesting that their event horizons were not just boundaries, but necessary cosmic guardians, ensuring that the predictability and coherence of the universe were maintained. Hawking's enthusiastic embrace of this hypothesis showcased his philosophical commitment to a universe governed by discoverable rules. It was a belief that even in the most extreme conditions, the universe had a logical, understandable structure, a belief that guided his entire career and inspired him to seek a theory of everything that would reveal the hidden order behind the apparent chaos of the cosmos. The cosmic censor, a conceptual guardian, stands as a testament to the elegant rationality that Hawking so passionately sought to prove. Chapter 8: A Brief History of Time, a cosmic bestseller. By the late 1980s, Stephen Hawking had already established himself as a preeminent theoretical physicist, a giant in the fields of cosmology and quantum gravity, but his name and his groundbreaking ideas were still largely confined to the academic world. The general public, while fascinated by the concept of black holes and the origins of the universe, had no accessible way to understand the complex, mathematical work that he and his colleagues were doing. This all changed with the publication of his book, A Brief History of Time, in 1988, a monumental and audacious effort to explain the most profound secrets of the cosmos to a lay audience. This book, a global bestseller, did more than just sell millions of copies. It transformed Hawking from a brilliant but obscure scientist into a worldwide cultural phenomenon, a living symbol of the indomitable human spirit. The genesis of the book was a deeply personal one. By the mid-1980s, Hawking's physical condition had deteriorated significantly. He had lost his ability to speak after a tracheotomy, a procedure that saved his life but silenced his voice. He now communicated through a computer-generated voice, using a cheek muscle to control a cursor on a screen. This physical isolation, far from silencing his intellectual voice, seemed to have focused it with a new intensity. He felt a deep sense of urgency to share his life's work with the world, a desire to communicate the profound beauty and elegance of the universe's laws to a wider audience. A Brief History of Time was an incredibly ambitious undertaking. It aimed to cover the entire sweep of cosmology and theoretical physics, from the Big Bang and the expansion of the universe to black holes, the direction of time, and the quest for a unified theory of everything, all in a manner that was accessible to a non-specialist audience. The book was famously written with the understanding that every equation, with the exception of Einstein's E=mc², would have its readership. This guiding principle forced Hawking to communicate his complex ideas through clear, elegant prose, using powerful analogies and a conversational tone that made the most abstract concepts feel tangible and relatable. He took readers on a journey through the universe's past, present, and future, with his own journey serving as a powerful, silent subtext. The book was an instant and global success. It spent a staggering 237 weeks on the New York Times bestseller list, was translated into dozens of languages, and sold millions of copies worldwide. Its success was due in no small part to the public's fascination with Hawking himself. The image of a brilliant mind trapped within a frail body, communicating with the universe through a computer-generated voice, was a powerful and inspiring one. He became a symbol of the triumph of intellect and spirit over physical adversity, a beacon of hope that the human mind, even in the face of unimaginable challenges, could still soar to the stars. The book was not without its critics. Some physicists found its explanations oversimplified, and its philosophical conclusions about the origins of the universe, while powerful, were still subjects of intense academic debate. However, its primary goal was not to be a textbook, but to spark curiosity and wonder. In this, it was a resounding success. It introduced a generation of readers to the profound questions of cosmology, inspiring countless young people to pursue careers in science and physics. It made black holes, singularities, and the Big Bang part of the popular cultural lexicon, bringing the universe's grand narrative into living rooms and classrooms around the world. The impact of A Brief History of Time was immense. It not only made Stephen Hawking a household name, but also changed the way science communication was approached. It demonstrated that even the most complex and abstract scientific ideas could be made accessible to a broad audience, provided they were communicated with passion, clarity, and a deep appreciation for the wonder of the cosmos. Break time equals 0. 25s/. The book stands as a testament to Hawking's intellectual generosity, his profound desire to share his life's work, and his unwavering belief that the universe's deepest secrets should not be the exclusive domain of a few brilliant minds, but a source of inspiration and wonder for all of humanity. It was the brief history that made Hawking an eternal figure in the history of science. Chapter 9: Time Travel and the Grandfather Paradox, a Cosmic Question. Stephen Hawking, ever a physicist who delighted in pushing the boundaries of what was considered possible, often delved into the captivating and mind-bending realm of time travel, a concept that has long been a staple of science fiction, but which he approached with the rigorous tools of theoretical physics. His inquiries into time travel were not just intellectual curiosities. They were an extension of his profound work on space-time, gravity, and the fundamental laws that govern the universe. He saw the possibility of time travel not as a magical feat, but as a potential consequence of the extreme warping of space-time, and he sought to understand the rules and, more importantly, the potential paradoxes that would govern such a journey. The idea of time travel, in the context of physics, finds its most plausible theoretical home in Einstein's general theory of relativity. Einstein's theory predicted that massive objects, like black holes, could warp space-time so severely that it could create wormholes or closed time-like curves, theoretical tunnels that could, in principle, connect different points in space-time, allowing for a journey through time. However, the physics required to create and stabilize such a wormhole would be astronomical, likely requiring exotic matter with negative energy density, a substance that has not been found in nature. Hawking, while acknowledging the theoretical possibility of these space-time shortcuts, was acutely aware of the paradoxes that would inevitably arise. The most famous of these is the grandfather paradox, a logical inconsistency that would seemingly render time travel impossible. The paradox, simply stated, asks, what if you traveled back in time and killed your own grandfather before he met your grandmother? If you were to succeed, then your parent would never be born, which means you would never be born, which means you could never have traveled back in time in the first place to kill your grandfather. The paradox creates a logical loop that is both fascinating and, to many physicists, a powerful argument against the possibility of time travel to the past. Hawking, with his characteristic wit and logical rigor, proposed a solution to this paradox, the chronology protection conjecture. This was not a proven theorem, but rather a conjecture, a plausible hypothesis that he hoped would be proven in the future. It stated that the laws of physics themselves conspired to prevent the formation of closed time-like curves, thereby forbidding time travel to the past on a macroscopic scale. He believed that any attempt to create a time machine would be met with an impassable physical barrier, such as a runaway feedback loop of radiation that would destroy the machine before it could be used for time travel. In essence, the universe itself acts as a cosmic sensor, protecting the integrity of the timeline and preventing the logical inconsistencies of the grandfather paradox from ever arising. Hawking's exploration of time travel was a perfect example of his approach to physics. Take a seemingly fantastical idea, ground it in the best available theoretical framework, and then use logical reasoning to explore its limits and contradictions. He recognized that the universe, in its elegant rationality, would likely have a built-in mechanism to prevent such a logical catastrophe as the grandfather paradox. His work on time travel, while not providing a blueprint for a time machine, was invaluable in formalizing the theoretical and philosophical debates surrounding the concept. It helped to move the conversation from the realm of pure fantasy to the more rigorous domain of theoretical physics, providing a framework for how future physicists might approach the problem. His popular writings and public lectures on time travel, including a famous time traveler's party that he hosted with no attendees, captivated the public imagination. He made the idea of time travel and the mind-bending physics behind it accessible to millions of people, using humor and a clear, elegant style to explain the most complex concepts. The grandfather paradox and the chronology protection conjecture became part of the popular lexicon, symbols of the profound questions that time travel poses. Hawking's work on this topic was a brilliant blend of serious physics and public engagement, a testament to his unique ability to communicate the wonder of the cosmos. He was not just a theoretical physicist, he was a cosmic storyteller, and time travel was one of his most compelling tales. His work on this topic, while unproven, gave us a logical framework for understanding the nature of time and its ultimate, and perhaps inviolable, laws. Chapter 10. The Origin of the Universe, A Boundless Beginning. Stephen Hawking, in his relentless pursuit of a complete understanding of the universe, dedicated a significant portion of his career to one of the most profound and challenging questions in all of science: the origin of the universe itself. He sought to find a coherent theoretical framework that could describe the very first moments of existence, a framework that would reconcile the singularity theorems he helped prove with the laws of quantum mechanics. His work in this area, particularly his collaboration with James Hartle on the no-boundary proposal, offered a radical and deeply elegant solution, suggesting a universe with no beginning, no end, and no singularity, a concept that fundamentally challenged the conventional Big Bang model. The standard Big Bang model, as supported by the Penrose-Hawking singularity theorems, described the universe as originating from an initial singularity, a point of infinite density and temperature. While this model was incredibly successful in describing the evolution of the universe from a very early, hot, dense state, it left the question of the beginning itself unanswered. What came before the Big Bang? What caused the singularity? The singularity was a point where the laws of physics as we know them broke down, making it impossible to describe the true beginning of the universe. For Hawking, this was a profoundly unsatisfying conclusion. He believed that a complete theory of cosmology should be able to describe the beginning without resorting to a point of breakdown. Hawking, along with James Hartle, began to explore a new approach, one that drew on the principles of quantum mechanics, particularly the concept of a path integral and imaginary time. In this highly abstract mathematical framework, they proposed a solution known as the no-boundary proposal. The proposal suggested that if you considered the universe's history in imaginary time, the universe would be finite in extent but have no boundary or edge. It would be like the surface of a sphere, which has no beginning or end but is still finite. When you convert this back to real time, the universe would still be finite, but it would have no singularity at its beginning. Instead of a point of infinite density, the universe would have begun as a smooth, well-behaved point, with no before the Big Bang, because there was no beginning to speak of. The no-boundary proposal was a radical departure from conventional thinking. It suggested a universe that could have arisen spontaneously from nothing, without the need for a cause or a creator. The laws of physics, in this model, were all that was needed to describe the universe's origin. Hawking famously stated, "So long as the universe had a beginning, it was always open to the possibility of a creator." He argued that the no-boundary proposal, by eliminating the need for a singularity at the beginning, eliminated the need for an external cause, providing a self-contained and elegant description of cosmic origins. The proposal was a masterpiece of theoretical physics, blending general relativity and quantum mechanics in a deeply satisfying way. It was a powerful and highly speculative attempt to find a theory of quantum gravity that could describe the universe's earliest moments. While the no-boundary proposal remains a subject of intense debate and is far from a proven theory, it has been immensely influential, providing a rich theoretical framework for cosmologists to explore. It challenged the very notion of a beginning, suggesting a universe that was eternally self-contained and boundless. For Hawking, the no-boundary proposal was more than just a mathematical solution. It was a profound philosophical statement. It was the ultimate expression of his belief in a universe that was rational, predictable, and governed by a set of discoverable laws. It was a testament to his intellectual courage, his willingness to challenge long-held assumptions, and his relentless pursuit of a complete, elegant, and unified theory of everything. His work on the origin of the universe, a lifelong quest that began with the singularity theorems and culminated in the no-boundary proposal, stands as a crowning achievement of his career. It gave us a new way to think about our own existence, suggesting that our universe, in its vast and infinite complexity, may have begun from a simple, elegant point, with no boundary or beginning to be found. His work on the origin of the universe was a final and most profound act of cosmic storytelling. Chapter 11. The Theory of Everything, the Ultimate Intellectual Quest. From the moment he began his postgraduate studies, Stephen Hawking was driven by the ultimate intellectual quest to find a theory of everything, a single, elegant framework that would reconcile all the fundamental forces of nature and provide a complete description of the universe. This quest, a modern-day holy grail for physicists, was a lifelong obsession, a profound desire to unify the two great pillars of 20th-century physics: Albert Einstein's general theory of relativity, which describes gravity and the large-scale structure of the cosmos, and quantum mechanics, which governs the subatomic world of particles and forces. This journey, while ultimately unfulfilled during his lifetime, produced some of his most profound insights and inspired a generation of physicists to pursue the same monumental goal. For much of the 20th century, general relativity and quantum mechanics existed as two separate, yet incredibly successful, descriptions of the universe. General relativity explained the motion of planets and galaxies with breathtaking precision, while quantum mechanics explained the behavior of atoms and light. However, they were fundamentally incompatible. When applied to the same extreme conditions, such as the singularity at the heart of a black hole or the Big Bang, their equations broke down, yielding nonsensical results. This breakdown was a sign of a deeper, more fundamental truth, that our understanding of the universe was incomplete. Hawking's work on black hole radiation was one of the first major steps towards bridging this gap. He showed that by applying the principles of quantum mechanics to the gravitational field around a black hole, you could get a physical, measurable effect: the emission of thermal radiation. This was a powerful demonstration that the two theories were not entirely independent, and that a deeper, unified theory was needed to explain the most extreme phenomena in the cosmos. He recognized that the ultimate theory would have to seamlessly incorporate both gravity and quantum mechanics, providing a complete, coherent description of the universe from its smallest scales to its largest. The quest for a theory of everything was not just a scientific pursuit. It was a deeply philosophical one for Hawking. He believed that such a theory, once discovered, would provide a complete and final answer to all the questions of physics. It would be a set of elegant, logical equations that would describe the universe's origin, its evolution, and its ultimate fate, all without the need for external intervention. He famously asked, "What is it that breathes fire into the equations and makes a universe for them to describe?" He hoped that a theory of everything would provide a final answer to this question, revealing the hidden rationality and order behind the apparent chaos of the cosmos. Throughout his career, Hawking explored various theoretical approaches to this problem. He worked on concepts like supergravity and later embraced the principles of string theory, a highly speculative and abstract framework that proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. String theory held the promise of unifying all the forces, including gravity, in a single, coherent mathematical structure. While he never fully committed to a single theory, His intellectual engagement with these ideas was a powerful engine for progress in the field. Hawking's pursuit of a theory of everything was a profound act of optimism. Despite his physical confinement, his mind was free to roam the infinite possibilities of the universe, searching for a single, elegant truth that would unite all of its disparate parts. He believed that this theory, once found, would represent the ultimate triumph of human reason, providing us with a complete understanding of the universe and our place within it. While a complete theory of everything remains elusive, Hawking's quest has left an indelible mark on theoretical physics. It has defined the central, unifying goal of the field, inspiring generations of physicists to pursue the same monumental task. His work on black holes, the origins of the universe, and time travel all contributed to this ultimate quest, providing crucial pieces of a puzzle that is still being put together. Hawking's legacy is not just in the answers he found, but in the questions he so brilliantly posed. He taught us to look for the hidden order, to seek the elegant simplicity behind the cosmic complexity, and to never give up on the ultimate intellectual journey. His relentless pursuit of a theory of everything stands as a testament to the power of the human mind, a final, beautiful act of cosmic exploration. Chapter 12. The Black Hole War, a Public Intellectual Joust. The world of theoretical physics, while often perceived as a solitary and quiet pursuit, is in reality a vibrant arena of intellectual jousting, passionate debate, and friendly rivalry. For Stephen Hawking, this arena was not just a place for abstract thought. It was a stage where he engaged in a long-running, public intellectual battle with some of the greatest minds of his generation, most famously over the information paradox. This captivating saga, known as the Black Hole War, was a high-stakes scientific drama that played out for decades, a testament to Hawking's intellectual courage and his unique ability to command public attention for complex scientific debates. The war began in earnest in the mid-1970s, after Hawking's groundbreaking discovery of black hole radiation. His initial conclusion was that as black holes evaporated, they destroyed the information of the matter that fell in, a position that directly violated a fundamental principle of quantum mechanics. This put him in direct opposition to a vast majority of the theoretical physics community, most notably his longtime rival and friend, Leonard Susskind, and physicist Kip Thorne. Susskind, in particular, was a fierce defender of the conservation of information, arguing that the universe could not be so fundamentally flawed as to allow for information to be destroyed. Hawking, with his characteristic stubbornness and intellectual rigor, stood his ground. He challenged his opponents with elegant, mathematical arguments and used his celebrity status to bring the debate to a global audience, making the information paradox a subject of widespread fascination. This was a unique aspect of Hawking's career. He was a public intellectual who could communicate the most abstract and complex scientific disputes in a way that captured the public's imagination. The Black Hole War was not just happening in obscure academic journals. It was a subject of conversation in popular magazines, television documentaries, and public lectures around the world. The pinnacle of this intellectual jousting came in the form of a famous bet. In 1997, Hawking and Kip Thorne, along with physicist John Preskill, made a formal bet about the outcome of the information paradox. Hawking and Thorne bet that information was lost in black holes, while Preskill bet that it was conserved. The bet was not for a large sum of money, but for an encyclopedia of information, a symbolic gesture that underscored the importance of the debate. This bet, a public performance of scientific disagreement, was a powerful way to engage a wider audience and show that science, at its best, is a human and dramatic endeavor. For nearly 3 decades, Hawking and his opponents wrestled with the paradox, proposing ingenious solutions and conducting thought experiments that pushed the boundaries of theoretical physics. The war was not fought with anger, but with a deep respect for the scientific process and a shared commitment to finding the truth. The debate was a powerful engine for progress, forcing the physics community to confront the deepest inconsistencies in their understanding and to search for a new, unified theory of quantum gravity that could resolve the conflict. It led to profound new insights into the nature of space-time, information, and quantum entanglement, insights that are still being explored today. In 2004, in a dramatic and public reversal, Hawking conceded the bet to John Preskill. He announced at a major conference that he had changed his mind and now believed that information was, in fact, conserved. He proposed a new, more nuanced model where the information, while scrambled, was not lost, but somehow encoded on the event horizon of the black hole. This reversal, a testament to his intellectual honesty, was a shock to the scientific community and a powerful message to the public that in science, changing your mind in the face of new evidence is a sign of strength, not weakness. The Black Hole War, though officially over, left a lasting legacy. It cemented the information paradox as one of the most compelling problems in physics, a problem that continues to drive a new generation of physicists to seek a unified theory of everything. It also showcased Stephen Hawking's unique role as a public intellectual, a man who could take a debate about the nature of quantum gravity and turn it into a captivating human story. The Black Hole War was a powerful reminder that at the heart of science, there are passionate, brilliant minds wrestling with the deepest questions of the cosmos, a struggle that, in Hawking's hands, was transformed into an epic saga of discovery. Chapter 13: Cosmic Resilience, the Triumph of Mind over Body. The story of Stephen Hawking is, at its core, a profound and inspiring tale of cosmic resilience, a powerful testament to the triumph of the human mind and spirit over the most profound physical adversity. While his scientific achievements in the fields of black holes and cosmology are monumental, his personal journey, a relentless battle against the debilitating effects of amyotrophic lateral sclerosis, ALS, is a saga of unparalleled courage that captivated the world and made him a global symbol of hope and intellectual perseverance. His life proved, in the most dramatic way possible, that the human mind, unbound by the limitations of the body, can still soar to the stars and unravel the deepest mysteries of the universe. Diagnosed with ALS at the age of 21 and given a prognosis of only a few years to live, Hawking's initial reaction was one of despair and withdrawal. However, his engagement to Jane Wilde and a newfound intellectual purpose in his PhD research ignited a powerful will to live and to work. As the disease progressed, slowly robbing him of his physical abilities, his ability to walk, to write, to speak, and eventually, to move anything but a few muscles in his face, his intellectual drive seemed to grow in inverse proportion. His mind became his only tool, a powerful, unencumbered engine for theoretical physics. He developed unique methods of working, relying on his formidable memory and his ability to visualize complex mathematical and geometrical problems entirely in his mind's eye. His colleagues would describe him as a kind of human supercomputer, a mind that could run complex calculations and thought experiments without the need for pen and paper. This mental discipline, born of necessity, may have even enhanced his unique approach to theoretical physics, forcing him to seek elegant, simple solutions rather than getting lost in tedious, written calculations. The loss of his ability to speak after a tracheotomy was a particularly devastating blow, but he was eventually given a computer-generated voice system, controlled by a cheek muscle. This iconic voice, with its American accent and robotic cadence, became his signature, a powerful and instantly recognizable symbol of his resilience. Through this voice, he was able to communicate his groundbreaking ideas, give public lectures, and write his books, including the global bestseller A Brief History of Time. Break time equals 0. 25s/The voice, once a technological necessity, became a vital part of his public persona, a testament to the fact that communication, even in the most challenging of circumstances, could be achieved through the ingenuity of technology and the power of the human will. His marriage to Jane Wilde, and later to Elaine Mason, provided crucial physical and emotional support, but his resilience was ultimately his own. He continued to travel, to give lectures, and to engage in scientific debate, pushing himself and the technology that supported him to its absolute limits. He became a cultural icon, appearing on television shows, in documentaries, and even in animated series like The Simpsons, using his celebrity not for personal gain, but to inspire people and to make science accessible. He became a living example of the power of the mind and the irrepressible nature of the human spirit. Break time equals 0. 25s/. The medical community was astonished by his longevity. He lived for over 50 years after his initial diagnosis, far surpassing all medical expectations. His case became a medical anomaly, a testament to the unpredictable nature of ALS and, perhaps, to the power of a life lived with purpose and passion. His resilience was not a passive endurance, but an active, vibrant, and relentless pursuit of knowledge and understanding. Stephen Hawking's life story, a parallel journey of physical decay and intellectual expansion, is one of the most inspiring tales of our time. He showed us that the greatest limitations are often not physical, but mental. He taught us that the human spirit, when fueled by a passion for knowledge and a love of the cosmos, can overcome almost any obstacle. His legacy is not just in his groundbreaking physics, but in his profound and enduring example of what it means to be human, to be curious, to be resilient, and to never give up on the quest to understand our place in the universe. He was a living testament to the fact that the mind, truly, is a universe unto itself. Chapter 14. Final Thoughts, the Legacy and the Future. In his later years, Stephen Hawking, a figure of global reverence and a living legend, turned his mind towards the grand, existential questions of humanity's future, often with a mix of optimism and somber caution. His final thoughts, expressed in his popular writings, interviews, and public lectures, were a profound culmination of a lifetime spent contemplating the origins and ultimate fate of the universe. He was no longer just a physicist talking about black holes. He was a cosmic philosopher, using his unique perspective to offer a vision of humanity's role in the vast, indifferent cosmos. His legacy in this final phase was one of intellectual generosity, a final act of guidance for a species standing on the precipice of a new technological and cosmological age. Hawking was a staunch advocate for humanity's expansion into space. He believed that our continued existence on a single planet was a perilous gamble, susceptible to a myriad of threats, from climate change and nuclear war to a catastrophic asteroid strike or a manufactured plague. He famously argued that humanity's best chance for long-term survival was to colonize other planets, becoming a multi-planetary species. He saw this not as a choice, but as a biological imperative, a necessary step to ensure our survival in a universe that, while beautiful, was often unforgiving. He championed initiatives like the Breakthrough Starshot project, a conceptual mission to send tiny, light-powered spacecraft to the nearest star system, Alpha Centauri, a project that was a powerful and public expression of his belief in humanity's destiny among the stars. He also offered stern warnings about the rapid advancement of artificial intelligence. While he acknowledged its potential to solve some of humanity's most pressing problems, he was deeply concerned about the prospect of a superintelligent AI that could outpace human intellect and, in a worst-case scenario, pose an existential threat to humanity. He argued that we should be cautious in our pursuit of AI and ensure that its development is guided by ethical principles and a deep sense of responsibility. This was a powerful and poignant message, coming from a man whose life was so intertwined with technology and who was, in many ways, a human-machine hybrid himself. In his final book, Brief Answers to the Big Questions, published posthumously, Hawking reflected on some of the most profound questions of our time. Is there a God? How did it all begin? Is there other intelligent life in the universe? He provided a final, personal, and profoundly moving summary of his life's work, blending his scientific conclusions with his philosophical outlook. He reaffirmed his belief that the universe could be explained without the need for a creator and that our existence was a product of the elegant, self-contained laws of physics. He ended his book with a message of hope and optimism, urging humanity to be brave, be curious, be determined, overcome the odds. It can be done. Hawking's legacy is a complex and multifaceted one. It is the legacy of a brilliant physicist who redefined our understanding of black holes and the origins of the universe. It is the legacy of a public intellectual who made the most abstract and complex scientific ideas accessible and fascinating to millions. And it is the legacy of a man whose personal story of resilience became a global inspiration, a testament to the triumph of the human spirit. The future of physics, cosmology, and our place in the universe will forever be shaped by Stephen Hawking's work. His questions about the information paradox, the no-boundary proposal, and the nature of a theory of everything continue to drive research and inspire a new generation of scientists. His final words, a call to action and a message of hope, serve as a guiding light for humanity as we face the challenges and opportunities of the future. Stephen Hawking, a mind that transcended the confines of his body, remains a permanent fixture in the cosmic narrative, a man who, in his quiet, resolute way, taught us to look up at the stars, not down at our feet. His final thoughts, a roadmap for our cosmic journey, are a gift to us all. The life of Stephen Hawking, a narrative of both profound intellectual triumph and heartbreaking personal struggle, stands as a monumental testament to the indomitable nature of the human spirit. From the devastating diagnosis of a young, brilliant man, a diagnosis that should have silenced his voice and stilled his mind, emerged one of the most powerful and influential intellects of the 20th century. His journey into the heart of black holes, a journey that was entirely theoretical yet profoundly transformative, not only redefined our understanding of these cosmic devourers, but also revealed a beautiful and intricate connection between the macro world of gravity and the quantum realm of particles. His discovery of Hawking radiation, a stunning blow to conventional wisdom, forever changed our view of black holes, showing them to be not eternal prisons, but dynamic, evolving entities that eventually evaporate. His legacy extends far beyond the confines of theoretical physics. He was a global icon, a public intellectual whose wit, humor, and unique voice brought the most abstract and complex questions of cosmology into the living rooms of millions. Through his best-selling book, A Brief History of Time, he inspired a generation of aspiring scientists and instilled a profound sense of wonder and curiosity about the universe in countless readers. His relentless pursuit of a theory of everything, a unified framework to describe all of the cosmos, defined his career and continues to inspire physicists today. But perhaps his most enduring legacy is the story of his own resilience. His long, courageous battle with ALS, a disease that should have claimed him decades earlier, became a powerful symbol of the triumph of mind over matter. He taught us that the greatest limitations are often self-imposed, and that the human spirit, when fueled by a passion for knowledge and a love for the universe, can overcome any obstacle. His iconic, computer-generated voice was not just a tool for communication. It was a beacon of hope, a testament to the power of technology and the unyielding strength of the human will. Stephen Hawking's life was a grand intellectual and personal odyssey, a journey into the deepest secrets of the cosmos that was mirrored by a profound journey into the depths of human courage. He was a man who, from the stillness of his wheelchair, saw the universe in its entirety, from its mysterious origins to its ultimate, silent fate. He reminded us that in the face of the vast and often terrifying scale of the universe, our own curiosity and our ability to reason are our most powerful tools. His final words were a call to action, a message to look up at the stars, not in fear, but in wonder. His legacy, a brilliant fusion of science and the human spirit, will forever resonate through the cosmos he so passionately sought to understand, a quiet, unwavering echo of a mind that was truly infinite.